Good morning, everyone. So, welcome to Operation Restart. So, the last meeting we discussed about states classification in Markov chain, right? I hope you still remember. So, in that topic, okay, we discussed various state classification, okay, whether they are irreducible, so with this mean strongly connected, yeah, or reducible, with this weakly connected or unconnected network, right? And then yeah, these are the examples, okay, of weakly connected, and this is strongly connected. Mean you can go from any point, okay, any node here to any other node. So this is strongly connected. Yeah? And sometimes the network will contain some kind of component. So component mean you have a strongly connected within this component. Okay, and then this is another component, right? But you see from this component 2, you can go to component 1, but cannot come back. So this is also still weakly connected. So this is called source component, right? And this is the sink component because this is the source where you can start your journey and then go to the sink. Yeah. So there is no sink node, there is no source node, but it's a component. So in linear algebra, we call this irreducible, but in graph theory, we call this strongly connected. Okay, so they are the same thing. This is in matrix, no, this is in network. And in Markov chains, okay, again, this is called irreducible Markov chain. Yeah? So means you can go from any state to any other state. Later today, we will discuss about regular Markov chain, which is strongly connected. Yeah? And then, so what is component? Again, component is strongly connected subnetwork, right? And they are basically create what is called equivalent class. Yeah? Equivalent class means it's the different name of component or strongly connected. Okay. Why it equivalent? Because from one place you can go to any other place because they are communicating to each other. Okay. And in Markov chain, okay, the node is represented as state. So the component is basically the subnetwork. There are two types of basin. Basin is basically the node that either sink or source. So how do you know it's a sink basin? If all the links are in to the node. So this is the sink basin. That all the arrow, there is only arrow in, but there is no arrow out. Okay? The same thing with source basin. This is only arrow out, but there is no arrow in. Okay, so source basin. And otherwise, practically just connect the node like this. Yeah? Oh, did you take the exam quiz today in Lentera?
Open at 10.
Eh?
The quiz for this class, right? For the
Yes,
Markov chain.
yes.
Yeah.
Finish.
It opened at 10. Yeah, I'm currently looking at it.
You want to do the quiz first, or we continue with this?
Oh, but you need to reopen the portal because.
Oh, okay.
Yeah, so maybe you can close it now. Later you can reopen.
Okay.
Because the quiz closed at 10 past 10.
Okay, sorry, I forgot. Okay, so do you want to show your drawing?
Okay, wait. I was a bit confused with the component and
Component and the node.
node. Yeah.
Okay. So try to draw. Okay. So look at this. This is source. That's correct. Okay. And then B going to C going to D, but D cannot go out from D, isn't it? Correct? Is this a component or not? From D, can you go to any other place?
You can go to C.
Yeah. So that means C and D create.
Oh.
Okay. C and D create a component, right?
Oh, okay, okay.
Strongly connected. So, but B does not create a component, because from B, so the sync node is the sync component is CD, correct? Not BCD. Yes, that one is a component because they can go. It's a strap there. Once go to C, can go to D, but cannot come back to B, right?
Oh, yeah.
Yeah, yeah. So, so the component is not B, but CD. Very good.
Okay.
Clear, yeah. How about the other one? Leafy, what is,
Wait,
okay, why you make a mistake?
yeah, I also confused with the component and the nodes. And
Okay.
so I switched them.
I see, I see.
Yeah, so at first I think the node is the component uh and vice versa. So that's why I got the wrong answer.
Okay, okay. So, strongly connected, when we said strongly connected network, that means the whole network. Okay. When we said component, that is only some part of it, some part of the network, so sub network. Okay. So, I hope this is clearer with this. So, is this quiz helpful? Now, you can see there in your drawing a while ago, okay, so you can see what is called absorbing. So there is a final class there. In Joy's drawing, there is a final class, right? What is the final class there? Which one is the final class in your drawing a while ago? So what is final class? Final class is absorbing class. So class means component, right? The CD a while ago, right? Once you go there, it's become a component. So CD become final class. It's not a node, right? It's a component. So you remember, okay? Final class is an absorbing class of states. Okay, so it's called final if no other class of state is reachable from this class. That means when reach this final class, it can never leave this final class. So is it clear? Your C and D a while ago, right? So how about this one? This is the, oh sorry.
Sir, I have a question. So the previous drawing, it has a final class, but no final nodes.
The node is not final. We call it absorbing node or sync node, right? So absorbing state, yeah, or absorbing node. So that is, if you go to the matrix, you can see the diagonal entry is 1. you look at the matrix and then you see that the permanent matrix is one, that is absorbing state, absorbing node or sink node. Okay, but when it become component, it's difficult to see because you cannot see that diagonal is not one and keep looping there inside that component. So in that case, you need to throw. Right. When you throw, you can see. Okay, so something like this. This is clearly absorbing node, right, or sink node, or absorbing state. Okay, I hope this is clear. So within that final class, okay, that process will return to the same state, right? So in your example a while ago, from C going to D and then come back again. So after a cycle, right? So there is some kind of period, okay? That means it will come back to the same every, for example, in your case, every 2 steps it will come back. Every 2 steps will come back to the same node, yeah, to the same state. So if you get the time, okay, so the greatest common divisor of the cycle length is called period. Okay, so that period is the same as for all states in that final class. Okay, so if the period is larger than 1, okay, so that is called periodic class. Okay, if the period is exactly 1, that is called aperiodic class. Okay, now what happened if you have your whole network is actually only one component. Your entire network consists only one component. That means your entire network is strongly connected. So that means, of course, that in that case you start to think, okay, will that state be visited again or not at regular number of turns? If yes, so there is some kind of period. Okay, so the state I have period D, okay, Di, meaning the number here. Okay, if the SII, that means the diagonal entry of the S exponent to K is equal to 0 whenever K is not divisible by D, and then D is the largest integer of this property. Yeah? So by definition, if you want to get the period, you need to get the GCD, greatest common divisor, of that period. Okay, so what is the exponent here? Okay, but if we use, this is mathematical definition, right? But if we use this definition to find the period, I tried that, it doesn't really work well, yeah? Because it's rather complicated to get this exponent. Okay, so in that case, there is another way. So this is an example. Okay, this is S. Yeah, you see here there is supposed to be period of 3, right? Because from A go to B, okay, from B go to C, and then from C go to A again. Yeah? You can check here S2, S3, S4, S5, X6. Yeah? So you see that when S3 they are all 1, 1, 1. Okay? S6 they are all 1, 1, 1. Right? So in that case, you can see the period is between 3 and 6. Okay? Of course, GCD of 3 and 6 is 3. Right? So you can see that they are repeating every 3. It will come back again. Okay? So then you need to find that GCD. Okay? That is the manual method. Yeah. So there is another way to do to find the period of Markov chain. Now, if the period of the state, okay, is actually irregular, okay, so then we call this aperiodic, or the period is equal to 1 because the GCD of irregular is 1, right? Okay, so one technique to calculate that is to use eigenvalue. Okay, so if Markov chain is periodic, the periodicity of the chain is given by the number of eigenvalues of unit modulus, meaning the modulus of that eigenvalue is 1. Okay, so here is the one that I use MATLAB. Okay, in MATLAB, you can get the eigenvalue using 8. Okay, say I got P in here is your transition matrix. And then you get the diagonal of that, and then you take the absolute value. Okay, and then you compare that absolute value with 1. So how many times it happened? That length is the period T. Okay, now I put it in Python. Okay, the same, exactly the same. Yeah. So in Python, you can use NumPy. Okay, and you get the eigenvalue. In NumPy, you will get both, yeah, eigenvalue and eigenvector. And then again, you take the modulus, the absolute value of the eigenvalue here. And then this code, unlike in MATLAB, so a little bit, you need to find one by one. Okay, so that means you look, yeah, over the element of this vector. Okay, so I get that element compared to the maximum of that. Okay, and you check if it is 1. Okay? So if the absolute value is near, okay, I put it less than a certain number, then add 1, and then I sum all of that, yeah? And then you will get the period. The same thing. Okay. Or maybe you can put this is equal 1. That's the same thing. Why? Because S is always stochastic matrix anyway. So that means that the maximum eigen value must be 1. Right. So with that, okay, you can check the, this is example of what is called periodic MC, Markov chain. So this is the, say if you start from any value like this, okay, look at this. I start from 0.7 here. It will come back again in 0.7 after 3 steps. And then again, come back here in 0.7 after 6, 9, and so on. So every 3 period, it will come back in the same state. Yeah. So look at this. That means it actually never converts, right? There is no convergent value. So because it's keep repeating in the same. But if you look at this, okay, the behavior will never convert to any value, but you can check the probability that they will visit here. Yeah, the probability they will visit that node. Okay, so if you simulate using, I think the code you did last week, right? This one. Okay, if you simulate that, okay, eventually you will see there is a convergent value. Yeah. Okay. There is some kind of steady state value. Yeah. And of course, if you input that steady state value inside, so this one, right? The steady state is 333. Yeah. So what will happen? You will get exactly flat. Okay, so it will become the stationary distribution. So this is equilibrium value. So that means the Markov chain actually converts. So can you see the difference between a limit distribution and the stationary distribution? Can you see the difference in this example? Or you can try first, maybe, so that you can understand. You have the code, right? All you need to do is to change this, right? So S, and then initially you can put any, say for example 0 0.1, 0 0.2, 0 0.7 and run it. You want to try? So that you can understand. Markov chain. So let me make the S. Right. This is the code last week that we made. So I'll just copy this. I will just put this S equal, what is the value? 0, 1, 0, 0, 0, 1, 1, 0, 0. Okay, let's do that. 0, 1, 0, 1, 0, comma, 0, 0, 1, right? Comma, one more, 1, 0, 0. Okay, and then so we can start with any value, the pi. So let me get the stationary distribution, can we? Okay, the stationary distribution is 0.333. If you run that, you get this. Okay, so now if I don't use the stationary distribution, but I use this instead. What is the value? 0 0.1, 0 0.2, 0 0.7. So 0 0.1, 0 0.2, 0 0.7. The total must be 1, right? So I don't use this. And if you run, okay, oops, okay, I missed one. Oh, okay, this is too much. Then only. There. So you can see every three steps it will come back. Did you get the same? So when you start from any probability value, not the stationary distribution, okay, it will come back to that place again. Okay, so every three steps it will come back here. Every three steps it will come back to the same state. Okay, but okay, if you calculate over time in the long period, how many times it will visit state A, how many times it will visit state B, how many times it will visit state C. That is what is called stationary distribution. So you get 33, right? 1/3. Okay, but in reality, it never converts to that 1/3, isn't it? Because it will always come back, okay, every 3 periods. Okay, compare that, for example, if you want, compare that to this example. Yeah? You see, it will convert to certain value, right? and that convergence or certain value, that is exactly the same as the stationary distribution. Okay. So if I run that, okay, stationary distribution, you see that will return the stationary distribution almost. Okay, this is and the last result. Okay, this is the stationary distribution. You will see they are almost the same. Right. So there is a convergence here. While if the period, if the value is aperiodic, it will go to certain asymptotic. Okay, but in this example a while ago, okay, this one is period 3. You see, the second example here, the period is 1, right? If the period is 1, it will converge. Yeah? If the period is not 1, you see, this is the period is 3, right? So you will see like this. Yeah? The stationary distribution is still the same, it is in this case 1/3, but that the meaning of stationary distribution here is not actually convergent value. Yeah, it's just the probability that how many times it will be visited. Livy, do you get the idea or not?
I don't really get it. No.
You don't really get it.
Yeah.
How about you, Joy?
Yeah.
You can help me to explain. Or you don't get it also. Okay, I will throw. If you don't get it, I will throw. Can you see my whiteboard?
Yeah.
Okay. So suppose you have this is A, B, C. Okay. This is the one that we just made a while ago, right? This is the one that 0, 1, 0, right? B to C. So 0, 0, 1, and then 1, 0, 0, isn't it? So you see here every 3, okay, from 1, 2, 3, come back A again, right? Every 3 will come back A again, right? So if you look at the behavior over time, this is time, okay? So this is A, this is B, this is C, for example. So if you start from A, okay, every 3, 1, 2, 3, yeah, it will come back to A again. Every 3, it will come back to A again. Okay, so the same thing, B, starting from B here, it will come back here every 3. C will come back every 3 also. Okay, so that means if you count what is the stationary distribution, it will not, you will not get the actual value of the node. Yeah, that means this is only happen how many times it will visit node A in the long run. Of course, because every 3, so you know this is 1/3. So up to here, you get it or not. Okay, so that stationary distribution is not really the equilibrium. Okay, this is only how many times it will visit. Okay. You got that? Okay, so the reality is that one is every 3 like this. So it will never reach the actual equilibrium. Now, if you, this is clear, yeah? So the next one is another, say A, B, C again, yeah? But this time it's not like this, but you get, say you get another one here. Okay, and you get another one here, and then you get another one here. So this is strongly connected. you have like this, okay, whatever probability you can put here, okay, what happen is, say start from, this is A, B, and C. Right? Starting from here, it will go different places, but eventually it will become asymptotic to certain probability. The same thing with the B, okay, starting from here, and then it will go, for example, this one. Okay. In the long run, it will go to certain equilibrium value. Okay. The value itself will go to certain number. Okay, that the stationary distribution here is not just the probability that how many times it will visit it. Yes, it is. Okay. It is the how many times it will be visited, but not only that, it has deeper meaning. Okay, it also have meaning that what is the actual value in here. Okay, so this will only happen if the period, okay, is equal to 1. That we call this aperiodic. Is this clear or not? Okay, so when you have a network, okay, if it is irreducible, irreducible, you understand, right? Irreducible means strongly connected, okay, and then if it is irreducible and aperiodic, then it will converge to a certain number. Okay, if it is periodic, okay, irreducible but periodic, it will not convert, but you can still get the convergent value. Okay. How about if it is reducible, if weakly connected, have some certain sink node, have certain source node or source component, sink component, then you cannot find the convergent value, not even the probability of that. Is that clear? So only when it is irreducible, when strongly connected, then you have two parts. Yeah? One is periodic or aperiodic. Okay. If it is periodic, okay, there is no asymptotic value. Okay, it's just the probability of how many times it will be visited. I hope it is clearer. Joy, Devi, what do you think? Give me feedback. Or still not clear? You ask again. What did you understand?
For the reducible one, can find the asymptotic state, because it will eventually like go on like A B C and then back to A B C again. And then for the one that we can find for the periodic and aperiodic is the irreducible one,
Yeah.
which is the strongly connected.
So irreducible have two, periodic or aperiodic. So the period is important. Yeah. So, but if it is reducible, reducible means weakly connected, right, or unconnected. So then you cannot find the asymptotic. You cannot even find the probability that we discussed here, the stationary distribution. Okay. Clear, yeah? So let's come back. Okay. Right. So this number here, okay, if you put inside, okay, it will become stationary distribution because you start with certain number. Yeah, that you can see you start with equilibrium, okay, it will come back to the equilibrium. This is another example of what is called aperiodic Markov chain. So how do you know this is aperiodic? Okay, when you multiply, okay, by itself, s times s, so s squared, right? So it's become positive matrix already. And then S3 is also positive matrix. So 2 and 3 GCD is 1, right? So in that case, it's clearly aperiodic. Okay. So the next question, something like this. So how about this? This MC, yeah, our Markov chain, is periodic or aperiodic? Yeah? If it is periodic, what is the period? Okay. Can you see? So if only looking this is difficult, but when you put it into that program, you can start to check the period. So here we can also do different way. Okay? So I multiply S2, S3, S4, right? Exponent. You can see S2 still have 0, S3 still have 0, yeah? S4 all positive matrix, right? It's primitive matrix. Yeah? So with that, we may think this is actually a regular Markov chain with period 4. Yeah? But actually, when you get the higher exponent, okay, they are all also positive matrix. Yeah? So for example, GCD of 4, 5, 6, 7 is all positive matrix. So in that case, the GCD of all of these are 1. Yeah? So in this case, this is also periodic. That's why I don't recommend to check using GCD. Yeah? Why? Because if you calculate like this, say, oh, you get the positive matrix already here, you are happy, maybe this is period 4, right? But you don't check 5, 6, and so on, and then it becomes wrong. Yeah? So the better way is actually to use that eigenvalue a while ago. So another type of Markov chain is reducible, so weakly connected. Yeah? So in that case, it has more than one equivalent class. Yeah? So when the Markov chain is absorbing, so that means contain sync node or sync component, right? So it must be reducible, okay? Because the process will be trapped in that absorbing state or absorbing component. Okay? And then when the Markov chains contain some source node, right, or contain sync state, again it will be reducible because it cannot come back to, yeah, to those states, right? So whatever you can see there is a transient state. You understand the meaning of transients? Okay? It can go out. Okay? So in that case, the chain is reducible. Yeah? Transient state means there is a source node or source component. Yeah? So this is example of reducible. Yeah. So why this one? Yeah, this is the source, right? It can go here, but cannot come back. Okay. So from here you can come back. Okay. Here you can come back. Okay. That means this is clearly a component, right? But this one is the one that is making it as a source. Okay. Now, one way to test irreducibility is to use this formula. Yeah? But be careful. Yeah? A while ago, I used S exponent n, right? But if you want to test irreducibility, you need to test using I plus S. I is the identity matrix. Okay, exponent n minus 1. If all positive, then the transition matrix S is irreducible. Okay. Okay, so if you want to use the code, I think I will make it. So you just get the array. Okay, so of course it must be square matrix, right? And then check, yeah, the I, that means the identity matrix, plus A, and then you exponent to the n minus 1. Yeah? N is the number of row or number of columns. Okay, and then if all positive, then it is irreducible. Otherwise, it is not. Clear, yeah? Okay, so with that you can see classification of Markov chain consists of two. Yeah? One is reducible and the other one is irreducible. Yeah? So irreducible can have 2 also divided by 2 again. That is based on absorbing state or final class. Yeah? This is component, absorbing component. Yeah? While the irreducible, you can check whether they are periodic or aperiodic. Okay, so the one that we call it irreducible aperiodic, there is another name. It's called regular Markov chain. Okay, so if it is periodic, we call this cyclic Markov chain. Okay, so yeah, this is the same thing. Yeah, the two-way to irreducible. Yeah, regular Markov chain. This is another test if you want to know if it is regular Markov chain or not. Yeah? By definition, okay, regular Markov chain means the transition matrix is primitive. That means exponent to S exponent to n is the number of rows or number of columns. It must be positive. Okay. Okay. So usually aperiodic irreducible. Okay. Now, if the period is larger than 1, that is cyclic Markov chain. Okay. This is example, just 2 state. Okay. So from A can go to B, and then B come back to A. Yeah. So this is periodic irreducible, right? It can come back. Okay. And the period is 2. How about this one? This one, from any state you can go to any other state. Okay, so clearly this is aperiodic, yeah? Because it's already positive in the diagonal. Right? So how about this? The test question is like this. It is reducible or irreducible? Periodic or aperiodic? Easy. Yeah? What is
It is irreducible.
Yeah, irreducible because you can go from any state to any other state. Periodic or not? Regular period come back to the same state or not? Regularly come back to the same state or not? If yes, periodic, right?
Yeah.
Yeah, from 1 it will go to 2, right? And then come back to 1 again, so periodic. Yeah? So every 2 will come back, right? So yeah, it will oscillate between state 1 and 2 indefinitely. Yeah? Yeah, for any initial state distribution, yeah, except for the stationary distribution 0.5. Yeah? Okay, so the oscillation period is 2, and because this is what is that? Because this is periodic, okay, you see that this will never become primitive. Okay, S exponent n will never become primitive. Can you see that? Sn and is like this if this is out, and if it is even become like this. So primitive matrix mean all positive entries. Okay, so it will never become primitive. any. So how about this? Irreducible or reducible? Period. What is the period? Always the same question. So this is really a component. From here can go anywhere. Yes, it can go anywhere, right? So from C can go anywhere. Yes. D can go anywhere. Yes. So this is clearly irreducible, right? And then you check what is the period. Yeah? So it's aperiodic because the period is irregular. Okay. Periodic is easy actually. It will come back to the same state again, exactly the same period. How about this one? Oh, this one. This one is also clear. What? Is this drawing correct? Zero 0.9. Oh, okay. So, okay. So this is irreducible periodic, yeah? Because every 2, you see, every 2 it will come back to this form. Can you see that? Every 2 it will come back to this form again. Okay, there is a period of 2. Okay. Anyway, if you put it into the equation, the program, you can get the period easily. Okay. How about this one? Oh, this one have what is this? What is state 1 in here? When you enter state 1, can it go out from state 1? Cannot, right? Yeah. Once you go here, it's here. So this is absorbing state. Yeah? So in that case, reducible. Yeah?
Sir, can I ask the difference between the absorbing states and the final class? What's the difference between
Oh, okay. So can you answer that? Good question. Can you answer that? What's the difference between absorbing state and final class? Okay. Absorbing state, okay, or sync state, sync node, right? So it's a node, one like this. Okay. When it is a final class, okay, it's a component. But be careful, one node is also a component. Okay. One node component can consist of one or more than one node. Okay. So component consists of one or more nodes. So in that case, state is only one. But when we say component, usually more than one, but one is also part of the component. Okay. And component means subnetwork, isn't it? Subnetwork can be only one node, can be entire network itself. Okay. Is this clear? Subset, you remember subset. Subset can be only one, everything, right? So here node 4 is source node. Oh yeah, node 4 is source node. Okay, node 1 is sync node. So in that case, clearly reducible. Yeah, reducible is aperiodic. So the same thing, yeah. How about this one? Okay. Oh, what is this? Node A is sync node, right? When you enter here, cannot go out, right? How about T? T is a source, right? Can go out, right? And then this is just a loop here. So this is a source, can go out, okay? Okay. But nothing going in except for itself, right? Okay. And this one form a component. Okay, so this one form a component, yeah. So yeah, node A is an absorbing state. Oh, this is a chain. Okay, if you have a chain like this, what will happen? Is this reducible or irreducible? From A can go to E? Yes. Right? From E come back to A? Can. Right? So it is irreducible. So the question is there any period? Right? So yes. Right? So every two, yeah, if you want to check, every two it will come back to the same form. Yeah, to the same form. Can you see the form, the pattern of 2 and 4 have the same pattern. Do you understand the meaning of pattern here? The pattern is the the positive entries in the same cell. Can you see that? The positive entries is in the same cell. That is what in the matrix, yeah, when we said pattern, that means the same positive entries in the same cell. So they have the same pattern. This one is not the same pattern with this, right? Because here is 0, here is positive. Can you get that? If you have any doubt, you ask question. How about this? Okay, so this is a network with the final class, yeah. So this is reducible clearly, yeah, because there is a final class, right? And this is the source. So if it is reducible and you want to check the period, okay, the period is always on the final class, yeah, not the source. In this example, exactly the same source. Every 4 will come back here, right? So, but this is, for example, this is only 3. You will confuse which one is the period. So the period is on the final class, not in the source. Yeah. Okay, so the test would be something like this. Yeah? So matching. Which one is which? Right? The test will be, so you match this one with that. Okay. So up to here, is there any question? So if not, I will go to the detail of, okay, the next slide, which is regular Markov chain. Okay, so this is where we can see the application. Okay. Many Markov chain is either regular or absorbing. Okay. So that's why we discuss special, yeah, here. Yeah. So, do you remember what is regular Markov chain? Irreducible, aperiodic. Okay. So, yeah, a non-negative square matrix is called primitive. Yeah, if there is an integer k, so that all the entries of a exponent k is positive. Yeah? So primitive matrix means there is some exponent, integer, that will make this positive. We don't know what is the integer k. So in fact, that is called index of primitivity. Yeah? So, but if there is some, if we multiply by itself, okay, meaning the exponent, up to certain integer, and they are all positive, then it is primitive matrix. Yeah, this is example. So I just multiply by itself. Yeah, this is S, A, multiplied by itself is all positive, isn't it? Right? So in that case, this is primitive matrix. Yeah? How about this one? Can you see? This is the one that you see that there is a period of 3 a while ago, right? Right? So this is non-primitive. Why? You see, I try A2, A3, A4, A5. Okay, it will never become positive, right? It will never become positive. So in fact, there is a cycle. Yeah, every 3, right? It will come back. Every 3. So this is A2, A3, A4 will come back to A, A5 will come back to A2, A6 will come back to A3, and so on. So this is the clear behavior of the cycle. Okay, so now let's define a regular Markov chain. So regular Markov chain is a if the S, the transition matrix, okay, has only positive entry for certain power R. That means regular Markov chain has primitive transition matrix. So another word it means it is irreducible aperiodic, yeah? Because no cycle, right? So again, how do you test irreducibility? You just use this formula. Yeah? Every time you see formula like this, what you will do is you check if you can make a code for this so that you can actually test. Okay. Okay. Can you test this is irreducible or not? If you don't want to use the code, you just throw. You can also throw. From any node, can it go to any other node? Yes or no? Yeah. Of course, when you have a very big matrix, very difficult to check, even if you throw. Yeah, if only 3, 4, you can throw easily and then you can check. So what do you think? So from here I can check A can go to B, right? B can go to A and C, and then C can go to any. So in this case, of course, this is irreducible. Right? The same thing here. So A can go to B, B to C, C to A, so come back. So this is, both of them are irreducible. Right? Both of them. But, okay. So if you use exponent, okay, you just exponent one time, you get already positive. Yeah? Of course, if you add with I, they are also positive. So this is regular chain. Yeah. You see, this is positive, so this is a regular chain, and it is irreducible. Yeah. Of course, when it is regular chain, it must be. Yeah. If it is a regular chain, it must be irreducible. Okay. How about this one? Okay. If you see, you multiply by S2, S3, and so on, it never become primitive. Yeah. Can you see that? Okay. But when you add with I, okay, exponent 2, it will become positive. Oh, okay. So you notice here, okay, this is non-primitive matrix S, but this is irreducible. In fact, this is irreducible periodic. So this is not regular Markov chain. Can you see that? Can you see the difference between regular and not regular? Both of them are irreducible, yeah, strongly connected. Right? Okay, so this is example of irreducible periodic. So in that case, non-regular. Clear or not? I just want you to distinguish between periodic and non-periodic. Yeah? So now, why regular Markov chain is important? Because using that you can get equilibrium value easily. Yeah. So if it is regular Markov chain, okay, you can get the stationary distribution using this formula. Okay, so this is the phi here is the equilibrium. Okay. Example, of course, 0 is always fixed point, yeah, for every transition matrix. And let's verify. Okay, say you have this S, and this is the fixed point. I said, don't believe me. Okay, so and then what you will do, you multiply. Yeah? Be careful, huh? This must be S transpose. Okay, so you transpose first. Yeah? Transpose means the same diagonal, but this one is reverse. Yeah? 0.3 is at the bottom. Yeah. Okay, and then you multiply by phi, it will come back to phi. Is this clear or not? Okay. So this formula, yeah, only happen for regular, yeah? Regular Markov chain. So and not only that, okay, there are some properties of regular Markov chain that is interesting. Yeah? So if you put that fixed point, the phi here, together, okay, up to n, let's call this another phi, but this is a matrix. Okay? So each column is this vector or fixed vector. Okay? So we call this limiting matrix. Okay? Now, this is the property of regular Markov chain. Yeah? If S is the transition matrix of regular Markov chain, right? So then the S transpose exponent K, okay, that limit, when K is very big, it will approach this limiting matrix. Okay? And then if you multiply any non-negative vector P, whatever P initial value, okay, this is the initial value, whatever you put, it will come back to the stationary distribution phi here. Okay. So this is very good property of regular Markov chain. Yeah? It doesn't care about your initial distribution. It will always come back here. Okay. And not only that, this fixed point is always positive, yeah? No zero. And not only that, this also unique. So there is connection between phi and S. For each S, phi must be unique. Okay. And this property will not happen for any other type of Markov chain. Yeah? If it is periodic, it will not happen. Yeah? If it is absorbing, it will not happen. Okay? Only for aperiodic irreducible. It is regular Markov chain. Okay? So this is the example, right? So check. Okay, this is S, and this is regular Markov chain. So if you exponent to 100, for example, you will see approaching the limiting matrix. You see, okay, and we know that the phi here, the stationary distribution is this one, and you see this is repeating of the stationary distribution. Suppose you get any p initial value, okay, and then you multiply that with p, it will come back to phi. And you see, this is unique. Yeah. Phi here, stationary distribution, is unique for each S. There is a one-to-one correspondence. So this is interesting. How about this one? You see, this is clearly, a while ago, we see this is periodic, right? Remember? So this is non-primitive, right? So this is non-regular. So let's exponent that to 100. Still like this, yeah? Non-primitive. Yeah? And then we know the stationary distribution is 1/3, right? Okay, when you put 1/3 into the phi here, 1/3, 1/3, 1/3 like this, okay, they are not the same as exponent 100, for example. Yeah, they are not the same thing. In regular, they are the same exactly. Yeah? But for cyclic, yeah, periodic, so they are not. Yeah? The same thing here. If you multiply by any p here, it will not become the original. Will not become the stationary distribution. Okay, so again, this is just to prove numerically. Okay, regular Markov chain is really something. Yeah. So there is what is called fundamental matrix, okay, of that regular Markov chain. Yeah? So if the transition matrix S is a regular Markov chain, then the following matrix inverse always exists. Okay, and this is called fundamental matrix. Yeah? So how do you get that? I, okay, identity matrix, minus S plus that limiting matrix transpose, and then you take the inverse. Okay, what does that mean? That means the total deviation from the equilibrium during the history of Markov chain. Yeah? And these are other properties of fundamental matrix. Yeah? Z here, the one that you calculate here. Okay, you can get a lot of different formulas. Yeah? And look, this formula only happen if you use regular Markov chain. So I give example in numeric. So this is the regular Markov chain. You get the phi, right? And then you put this into the limiting matrix. You just copy, okay? And then you calculate the z. Okay, this is the z. And then I just show in the formula that they are actually proof numerically, yeah, all of this example of the properties. Okay, so one practical application is to test whether stochastic process is dependent or independent. So if they are independent, then the fundamental matrix will be identity matrix. So that will happen when S is actually the same as transpose of the limiting matrix. Okay, so with that, we can go to the next one. Up to here, is there any question? So basically, if I want to conclude, regular Markov chain with this irreducible aperiodic is special. Okay. Now, if you can use in your application, yeah, if you can direct your application toward this one, okay, then you will have something because of the spatial properties. Yeah. Next, let's go to absorbing Markov chain. Yeah. This is the last part of Markov chain topic. So, you know, there is some final class in the absorbing Markov chain, right? Or absorbing state. Okay, so a state K, yeah, in a Markov chain is an absorbing state if it is impossible to leave it. Right? So how do you see KK, meaning that the diagonal entry is 1, okay, while the others is not. Okay? So Markov chain is called absorbing chain if it has at least one absorbing state. Yeah? And then from every state, it is possible to reach that absorbing state. Yeah? If it is unconnected, they are not absorbing state. Because, yes, there is a absorbing state, but you cannot go from other state to that absorbing state, then this is not absorbing chain. Is it clear or not? What I mean? Let me draw so that you will understand. So this is example of absorbing state, right? See, we go here. See this one, yeah? This is A, B, C, D. Yeah? The A is absorbing state, right? But, okay, so this is an absorbing chain, the whole thing. Chain is the network, right? But now if I have another one here, for example, this one is E and F, okay, and the whole thing is one network, that means that this network is unconnected, isn't it? Right? Because from E, you cannot go to C, right? From F, you cannot go to A. So in that case, even though you have absorbing state, but the second, this is N, right? So from every state, it is possible to reach some absorbing state. It is not, right? So in that case, because this is unconnected, so in this case, this is not absorbing chain. Yeah, it must be connected. So if you connect this, yes, it will become absorbing chain. Clear? Okay. So in reducible Markov chain, okay, if the state is not absorbing state, it is called transient state. Yeah. So transient state means you can go out. There's a probability that you stay here. Okay. So for example, from E you can go to F and then come back to E, right? But once you go out of this to C, you cannot come back, right? So that state is transient because once you go out, there is probability that you cannot come back. Okay. So how do you know, okay, if it is reducible or absorbing? Okay, the way to do is to check. Okay, if you permute your matrix in such a way so that you will have something like this. This is the form. Okay, so this is called standard form. Okay, so that one of that is 0 here. Okay, if you have a matrix that you can permute, meaning you exchange the row, you exchange the column, yeah, in such a way so that you can get this form, okay, with certain 0 there and identity matrix here, right? And then R and Q is just any matrix with okay, non-zero with some positive entries. Okay, some positive entries. In that case, this is called absorbing Markov chain. So the difficulty here is actually to create that permutation so that you can get this. Okay. Let's assume for a while that you already get this. Okay. If you get this form already, then you can calculate Q. Based on the Q and R, you can calculate fundamental matrix N and P. Yeah. So remember, yeah, first you need to get the standard form of the absorbing Markov chain. Okay. So in that case, you can get the R and the Q. After that, okay, from that you can calculate the I minus Q in first, and then N minus multiplied by R, you can get P. Okay, so will the process actually reach an absorbing state? Yes or no? That this is the four questions that usually ask, yeah, for the absorbing state. What is the average number of time we will expect the process to be in one transient state if it is start in another transient state, and then what is the average number of steps before the process enter the absorbing state, and then what is the probability that the process will be absorbed to that particular state if it start from any transient state. So let's check this. Yeah. Yes. Okay. In any absorbing Markov chain, okay, every absorbing Markov process will eventually reach the absorbing state, right? Okay, and then it will be trapped there. Okay, if you see the Markov chain with absorbing chain, okay, that you will see that eventually it will be trapped there. Okay, and then the number N is coming from here, this one, okay, the fundamental matrix. Okay, so the number Nij, the entry, is the average number of times, okay, the process will be in the J transient state if it starts from I. So this is the meaning of that fundamental matrix. Okay, and then we can calculate the matrix T. Okay, T is the average number of steps before the process enter an absorbing state. Yeah? So that T is the sum of the entries in N. Yeah? Ti here is the sum of the entries in row I of matrix, fundamental matrix. Okay, next, the number B, Bij, is the probability of eventually entering J absorbing state if the process starts from I transient state. What is this B? B is the N times R here. Okay. Seems like complicated, right? Okay. Baby is laughing. Okay, so let's do the example so that you can get, okay, the meaning. Okay. Okay. So this is an example. Say academic review, okay, of the contract of all faculty members each year, right? So the rule of the university demand that a professor must be tenured to be continued, okay, but all other faculty member must be fired, okay. So if the faculty member is not fired, then it may be kept on for another year on the same rank or promoted to a tenure position, okay, or promoted but not given a tenure. Do you understand the meaning of tenure? permanent position. Okay, so if I want to explain this, if you work in a company, in this case in university, there are two things. Yeah, one is you are kept as a contract worker, and the other one is as tenure. Okay, but in the beginning you are just based on contract, right? So in Indonesia, the tenure position usually after 1 year. Yeah? In the Philippines, after 3 years. In the US, it's after 7 years. That's crazy, right? Okay. So if you are working up to 7 years and you cannot get tenure, meaning you are not get promoted into permanent position, okay, then you will be fired. Clear? So that's why here. So probably you can continue, okay, up to 7 years. Okay. So or you will be fired. Or the next year you can continue the same rank or promoted to tenure position, or promoted but not given tenure. So there are 4 possibilities here. Okay. So if the professor is promoted, not given tenure in the previous year, the next promotion must be a tenure rank. Okay. So life is so pleasant in this university, and the job market is this much that no one leaves the school voluntarily. That's the assumption. So that means and everyone either fired or given a tenure. Right. So in that case, you can see the matrix is something like this. So F, yeah, the state of the employment categories of individual at the end of particular year. So this is the row is this year, the column in next year. Okay, F is fired. Promoted to tenure rank is T. T is tenure. Right? Promoted but not given tenure is P. Okay, and then retained untenure rank without promotion is R. So in that case, we know, okay, if it is fired, it's always fired, right? If it is tenure, always tenure, right? So 1 probability. Yeah? The others are not known, and then there is no P to P, right? Meaning, if you are promoted but not with tenure, it's not possible. So that's why this is 0. Right? All the others are numbers, so A, B, C, D, E, F, G are numbers, positive numbers. Clear? But if you look at this example, this is already arranged in such a way so that you can get this is what this matrix. This is the R, this is the Q, correct? A while ago, do you remember the form? This is the R and the Q. And this is identity matrix, and that is 0. Yeah, I will show you again. So this is identity matrix, and this is 0. Right. Okay, you get the form now. So you know the R, you know the Q, right? Up to here first, is it clear or not? Livy, Joy? So you know the R, you know the Q. Okay, so once you know the R and Q, there, matrix R and Q. Okay, so which one? Yeah, state F and T are absorbing state. Yeah? Right. Once enter there, you cannot leave. Right? How do you know it's absorbing state? Easy. This one is 1. Right? In the diagonal matrix is 1. That is absorbing state. Right, you remember that. Okay. So, okay, now let's put that number. Yeah? So, say we have this number and then initial distribution. So, this is initial distribution. Yeah? T, R, and P is given. So, how about F? F is 0, right? In the initial distribution. Yeah. So, and what is the distribution? Yeah? 5 years later. Right. So this is the initial distribution. Okay, we want to find P5, right? So yes, we can calculate P5 using this formula, right? This is the formula of Markov chain, right? The one that you put in your simulation, your code, right? This is the one. Okay, so you get that. Okay, so in this case, because initially we have 100 easily, yeah, 100 faculty. So you know, okay, 5 years from now, 19 will be untenured, right? Will be fired. 29. Oh, this is 29 supposed to be. Sorry. Oh, will be advanced to a tenure run. Okay, so in that case, the total is 59, right? And then 17 will be retained, and then 5 will get promotion without tenure. Yeah, the P. Right. So, do you get the application? Now, we can go further, okay? Find the R, Q, N, and P, and then interpret the result. Then you can start to calculate this. R is clear, yeah? This is R, right? And then this is Q, right? So, and then from R, you can minus, yeah, I minus Q, okay? And then you take the inverse, you get the N. This is the fundamental matrix, yeah? And then you multiply N with R, you get P, okay? Okay, you get that number, so what, right? Okay, so that is where we will start to get the meaning. Okay, so we see that every non-tenure faculty member will eventually get promoted or tenure. Yeah? How do you know? Because of the this one, right? Because it's absorbing, right? Second, the faculty member who just been promoted but not given the tenure, that means initially state P, okay, it will eventually will given tenure with probability of this number. Yeah, what is this number? Come from P, yeah? P22. Okay? P22, this one. Okay, so and then all will be fired with that probability of P21. Yeah? This from P, it will go to fire with probability of 30%. Okay. From promoted and then become tenure with this probability. So we get the probability, okay, from one state to another. Okay, and then now you want to get the expected waiting time, okay, before they get professorship, right? So now not only the probability, now you can also get the time, okay. On average, what is that? T2, okay. T2 is of course the sum of the row, okay, of n. Yeah? So in that case, n21, this one plus this one, right? So you sum, you get 3.77. Yeah. So on average, the people need to wait almost 4 years before they get professorship in that university. Okay. And then now a professor who was retained in her present rank, okay, by the committee this year, initially, right, will face probability of say 49% eventually to gain tenure and probability of 50% that will be fired. Okay. That come from this one, right? Yeah. So if you start with R, 50% will be fired, 49% will be tenure. Okay, so this one. Okay, and then the expected waiting time is, yeah, of course, N11. Yeah, this one. You add. Yeah, with this 5.5. Yeah, 5.5 years. So this is the example of application. Markov chain. So yeah, so this model actually cannot predict what happened in that untenured professor during 5 years. Yeah? So, but it is actually still a useful tool, right, for planning and decision making. Yeah? So, if you know this, what happened is you start to create a policy. Yeah? Probably you want to change this result, or you want to do something to how many faculty, yeah, you will hire, or how many faculty you will remove within certain number of years. In this example, in faculty, but if you're using company, you can also do that. Yeah. So the same thing with the society. Yeah? The number of population, for example, how many people will eventually die. For example, absorbing state, right? Die. Okay. Or how many people eventually get married, for example. So that's absorbing state. Okay. Or how many people eventually divorce. So that is eventually you get certain absorbing state that you can do. Those are the applications that you can check, and how long it will get into that absorbing state from curl state. So yeah, so if you check the stationary distribution, okay, eventually you will get this value using simulation. Okay, using simulation you will get this value, but if you use linear algebra, okay, the one that you probably make it in Python, it will generate error. Okay, why? Because the inverse matrix, the general inverse, does not exist for absorbing chain. Okay. Try this if you want. You can try this for practice. So, can you calculate the stationary distribution, and can you simulate this? Okay. You have your Python code, right? So you can get the simulation of this. I think that's the if you try that, okay. So this is what I'm using, right? So the stationary formula, yeah, distribution formula cannot be used, yeah? Because this is only for irreducible. Yeah? This formula only be used for irreducible. So in this case, the Partial distribution will generate error, but you can still simulate. Yeah? When you simulate, you will get this result. Okay, you can try. So after lunch, we discuss about the application of regular Markov or irreducible Markov chain. So we call that ideal flow network. So that's the next slide. Try this one first. I hope you can try this. At least by trying this, you can get certain understanding. So next week is the final the last week our semester. So please present your project. Okay, the last one. I will put the entries in Planetera later. So it will be very hectic time. Do you want to share your screen?
Sir, for the pi, what number should we use?
The pi. Oh, any. Sorry. The pi you can put start from any number.
Also any number.
Yes. Initially you can put from any number. And then after you get the stationary distribution, okay, then you can get back again that stationary distribution, and then you input again so that you can get the stationary to check whether that is really stationary.
Sir, mine shows can multiply sequence by non-integer of type float.
Hmm? Can you share your tab error line 6? Where is line 6? Hmm? P is P dot. Okay. Let me check. Simulate. Okay, and then S and P and array P and append and then NP dot P. Yeah, okay, so this is correct. And which maybe the which P you want? Which file? 20. The one that you use is 27 or 26. So if you try with the 26 first, does it work? Okay, 26 first you open and then 27 you close. Does it work? Is it working?
No, it worked just
No?
fine before.
Really? Oh, maybe certain things that you did not put. So 1, 0, 0, 0,
Yeah.
1, 0, 1, and then 0 0.1, 0 0.00. Okay. Oh, the, and then 0 0.05, 0 0.5, 0 0.5, and 0. What is strange? Oh, 1, 2, 3, 4. I do not see any problem.
I think the third row of S. You put like
Oh yeah, maybe
yeah,
can you put
the
the
no the comma there.
one? I think 0 point. Yeah, that one. 0 point, and then after that is wrong, right? Your 0 there is incorrect.
Oh, this one. It's
Yeah. No, no,
yeah,
no.
yeah.
After
It's
zero
an
point 0.1,
extra
after 0 0.1, you have extra 0 comma.
yeah.
So, okay, now working. Oh, P. Where is what is P? P in line 39.
Did I put?
Oh,
Oh, this one.
okay. I think it's fine now. Okay, it works, right? Does it work?
Oh, this one. Yeah, it works. Okay.
Yeah, it worked, right?
Yeah.
Ah, yeah, that's good.
I don't bring the.
Okay,
Okay. Okay. Thank you, sir.
thank you. Yeah. How about you, Livy?
I got big number here. I don't know.
You want to share your screen?
Here.
Oh, you got it, yes. Okay. Very good. So, yes. If,
It's so big. Yeah.
yes, yes. You can get the last part only if you want. Uh, in that case, you can do the approximate result.
This one.
Okay, I will share my screen so that you can see. Okay, let me share my screen. So you can do like this. This is the result, right? And then you can get the approximate result. Line 151. That means you get the last column only. So for all rows, for the last column only, right? And then that is the one that you print. Yeah. In this case, I round to six number of decimals. This 2 is the one that you probably need to add so that we can get the approximate, yeah, of the stationary distribution. Okay, so with this, the Markov chain finish. Okay, what you get here? What is that? What is the meaning of that result that you got? Yeah. Eventually go to the two absorbing state, isn't it? With that probability. Yeah? The last two are 0, 0. That means it will go out from that. Yeah? It will come back. It will always go to the absorbing state. Right? Okay, so let's stop for a while and come back again at 1 o'clock.